Okay, this is going to be the first lecture of in a new subject called Algebraic Topology. All topologies, all different versions of topologies, you'll see there's a bunch of different names. There's combinatorial topology, there's geometric topology, there's algebraic topology, point set topology. There's probably a lot of topologies I don't even know about. They tend to all they all seem to lean on point set topology, though. Right? Point set is sort of your foundational concept of topology, and that's what we've been discussing, is point set topology. But now we're going to talk about algebraic topology, and specifically today we're going to talk about homotopy. And this concept of algebraic topology and homotopy, the whole point of these things is that we start using group theory. So there's really no point in listening to this lecture unless you feel like you have a nice fundamental understanding of group theory. I don't want to say you have to be an expert in it because it's a pretty vast subject and it's got a lot of nooks and crannies, and certainly you don't need to know all of it, but you certainly have to understand a couple things. You need to know what a group is, the definition of a group. You have to understand homomorphisms between groups, homomorphisms. Now notice this is not homeomorphisms, right? Not homeomorphisms. Homeomorphisms are between topological spaces. Homomorphisms are maps between groups. You've got to understand what homomorphisms are. In particular, you need to know what the kernel of a homomorphism is. It would be good to understand the notion of a normal subgroup, right? A normal subgroup. Well, you certainly need to understand the notion of a subgroup. You should understand the normal subgroup. You should understand how that's the kernel of a homomorphism for the quotient group, right? For the quotient group. That's a good thing to know. If you know those things, these are sort of, if you finished any kind of course in group theory, you'll know these things. And third, you need to know, well, certainly what an isomorphism is. Just a sort of a super special case of a homomorphism. A homomorphism and an isomorphism in group theory are, well, I guess an isomorphism is somewhat similar to a homeomorphism or a diffeomorphism in our topology studies. A homomorphism is a map from one group to another that's not, it's not literally one-to-one and on-to, but it still preserves the group structure. Groups have a lot more structure, I think, than topological spaces, although that's arguable. Anyway, this is the prerequisite knowledge, really, for what we're going to talk about in homotopy. We're not going to need necessarily this stuff right away here, but it's all part and parcel. If you understand homomorphisms, you're probably going to know about these things as well. Okay, so with that in mind, we are going to begin. So let's start by talking about some topological space X. And I will draw it like this. And this will be the topological space X, so it's the set X with its topology. And we're going to consider a pair of points in X, say a point A and a point B. And now we're also going to talk about a line segment, the real line, but we're going to just talk about the segment from 0 to 1, and a map. And we'll call that map gamma 0. We're going to talk about a couple different maps. So I'm going to start with the map called gamma 0. And we know this from our previous work that when you have a map, such as gamma 0, which goes from 0 and 1 into a topological space X, that's called a curve. And, of course, it's got to be a continuous map. But all these maps are continuous, right? From now on, I'm not even going to bother saying that. And so, but this map has a particular property that f of 0 is A and f of 1 is B, and the curve goes from A to B, like that. You know what? I'm going to make the curve a little bit more of a There you go. I'm going to make these 2 points big because I'm going to use some other colors here. So this is your basic curve. Now we talked a lot about curves when we talked about tangent spaces. There's really nothing different here except that these we're focusing this curve to be specifically from on this closed interval, right? This closed interval. So by the way, this curve contains its endpoints, just so you understand. So because it contains its endpoints, the complement of this closed curve is this entire space missing that curve, which is actually an open set. So the complement of this curve is an open set, so the curve is actually closed. Not that important for what we're talking about, but just so you understand, it does contain the endpoints. Okay, so once we have one curve in this space, we can certainly describe another curve, which I'll do down here, and it gets its own interval from 0 to 1, and we'll call that curve gamma 1. And it will start at A, and it will go to B. Okay, so there's two separate curves, gamma 0 and gamma 1. And I could actually, at this point now, write, instead of that, I could write gamma I, where I is equal to 1 and 2. Or it's not 1 and 2, 0 and 1. 0 and 1. So now, I could also, by the way, do this with a third curve. I could easily make a third curve here. I could make an infinite number of curves, clearly, between 0 and 1, or between A and B. But we now want to talk about the relationship between curves like this. And that one of the relationships we're interested in is the one we're going to call homotopy, or curves being homotopic. And the idea in topology has already been, we've already seen that we take a topological space like X and we have open sets and we can deform those open sets into another topological space. And if there's a homeomorphism, we're basically just sort of taking a space and reshaping it into some other space that's very, very similar. In fact, it's identical under the notion of topology. Homeomorphisms is a sort of identicalness, but it has to do with distorting a space by distorting its open sets into the open sets of another space. So this notion of distortion we're also going to now apply just to these curves that are inside a single space. We're going to say, hey, this curve here, this curve gamma 1 or gamma 0, can I distort that curve, continuously distort that curve so it becomes gamma 1? Can I sort of move that curve point by point smoothly through the space X, one-to-one correspondence, continuously doing it so that gamma 0 becomes gamma 1. And that's the idea of homotopic. If you can do that, then your two curves are homotopic. And the idea is to formalize mathematically kind of how that might be done. And so we're going to, maybe I should put it in green, right? We can indicate that this curve would slowly change into, say, that curve, and that curve, and that curve. Then ultimately it changes into this curve, and it always begins at A and ends at B, but it slowly converts itself from gamma 0 to gamma 1. You can we literally want to imagine each of these as being, say, gamma 0.1 and gamma 0.2 and gamma 0.8 and gamma 0.9, and then the last one, of course, is gamma 1, and it started at gamma 0. So there's all these little curves that are indexed from 0 to 1. And in fact, we're literally going to do that. We're going to create curves, or we're going to create a function of curves that uses an index of that nature. All right, so let me take this drawing and sort of move it aside, make it a little bit smaller, and move it aside. And now we're going to talk about the actual homotopy. So the notion of the homotopy is it's a function, and it's a function of two variables, s and t. T is the variable that's going to describe which curve. And S is going to describe, it's a parameter, I'll call it. Well, they're both parameters, really. But I like calling this a parameter because in general relativity, we use parameters along world lines. So where you are on a world line is given by the parameter along the world line. So I'll call that so this So T, in general relativity speak, T would represent which world line you're on, and S would represent where you are on that world line. But in this case, we're talking about which curve you're on, and S is where on the curve. Right, and so I'm just talking really about when I connect it to general relativity, I'm just talking about the use of the word parameter. But the word parameter is where you are on a curve in general relativity. So I'll call S the parameter in this case, just to keep that language. So someday we'll get back to general relativity here. So, so I could actually write another form of notation, which is very common out there. Gamma of T of S is actually defined as F of S of T. And gamma of T of S is going to be each of these curves in here, because T is always going to be less than or equal to 1 and greater than or equal to 0. And in fact, same with S. S is going to be less than or equal to 1 and greater than or equal to 0. And we can think about S as this parameter, as the parameter that drives us from 0 to 1 in the domain of these curves. And T is basically which curve you're on, right? So there's a smooth transition of all these different curves that go from 0 to 1 into this space. And T kind of monitors that. So now if I want to just sort of draw this again with A here and B here, and then I have gamma 0 of S like that, and I guess since I'm doing red, I'll stick with red, and I have gamma 1 of S like this, then each of the curves in between, let me just draw, say, a couple of them like this. If I start with a certain value of S, that puts me right here on gamma 0, so I now have literally gamma 0 of, well, let me write it this way. Let me write it as gamma 0 of some number S, some number S0, right? And then I slowly start changing T. Then as I change T, it's going to move over to some point here, gamma, let's call that 1, let's call it 1/4, gamma 1/4 of S0, and then this would be gamma 1/2 S0, and then this would be gamma 3/4 of S0, and then ultimately be gamma 1 of S0. So I'm moving that one point through all of these curves that are defined by F of S of T, and I'm moving each point from the curve gamma 0 to the curve gamma 1, and I can do this for every single point. And I can slowly, if I define these intermediate curves well, I can slowly basically take every point here, turn it into every point there, continuously, and which means I don't break the line. I can stretch it and compress it, but I don't break it. And because we can do this, we say that gamma 0 is homotopic to gamma 1. And in fact, it's obviously homotopic to every single curve in here, right? Gamma 0 is going to be homotopic to gamma 1/4, gamma 1/2 is going to be homotopic to all of those curves. And it's also homotopic to curves that aren't shown here, right? If there's a curve like this, gamma 0 is going to clearly be homotopic to that one too, right? So just because we've created a homotopy doesn't mean we've identified every curve that's homotopic to every other curve. We've just identified that we've proven that gamma 0 is homotopic to gamma 1 because we've created this function that slowly converts it from one to another. That is the symbol we use for a homotopy, is gamma 0 is homotopic to gamma 1. And some things we want to remember is maybe facts that should be somewhat clear at this point, but F of S of 0 equals gamma 0 of S. F of S of 1 equals gamma 1 of S, right? So these are two ways to write these functions, right? These functions here are actually curves. These are homotopies, right? These are the homotopies. So each of the curves is sort of embedded in these homotopies. These here are families of curves described by two parameters. And this is one curve described by the parameter S, but identified by this subscript 0 and 1. And there are all of these subsequent curves that exist in this family that have numbers between 0 and 1. But likewise, f of 0 for every member of the family, right? So what this says is the position on the curve that corresponds to s equals 0 for any member of the family with t as their identifier of the particular curve, right? 0, 1, or anything in between like that. That is always going to be A. And likewise, f of 1 of t is always going to be B. And this is a statement that all the curves in the homotopy start at A and end at B. And that's really important, right? That's the whole point of deforming the curves, is they start at A and end at B, is they're all homotopic to each other. Now, by the way, clearly you don't necessarily, that's not the only interesting phenomenon for curves, right? They wouldn't all have to start at A and end at B. You could ask this question. You have A and B, and then you have C and D, and you have some curve between C and D, and you have some curve between A and B. You could ask about the connection like this, right? Between those two curves, even though they don't start at A and B, all right? So there is a form of homotopy that has to do with that, and we'll talk about that later, but that is not what we're talking about right now. Right now we're talking about homotopic curves with fixed endpoints. All right, so now that we have that idea in place, we can say a few obvious things, right? If we are sitting in R2, right, in the plane R2, and I have a point A, and I have a point B, and I connect it, R2, by the way, with the usual topology, right? And I connect it with a curve. It's pretty intuitive, I think, that any other curve that connects A and B, no matter what it does, by the way, it can cross, right? That those two curves are going to be homotopic, right? That's pretty clear. And in fact, it's easy to prove. And there's a lot of proofs in this that I'm not going to do. I'm just going to sort of describe the subject. This isn't a full-blown course in homotopy, but you can certainly, once you sort of understand what they're talking about, you can kind of walk through these proofs pretty easily. They're not very complicated. So there it is pretty clear that all curves between A and B are homotopic, which kind of takes the punch out of what this might all mean. If every curve is homotopic to every curve, who cares? But that's a property, of course, of R2, right? R2 has this interesting property that any curve connecting any 2 points, A and B, are going to be homotopic. That's not going to be true for all spaces and all curves in all spaces. The whole point of algebraic topology is to sort of look at every space and see what kind of curves can exist in that space that are homotopic to each other or not homotopic to each other. And R2, nice simple space, all the curves are homotopic to each other. So we understand it to be a simple space in some sense because the simple nature of the simple point that all curves are homotopic. So we are now seeking a way of characterizing all the different types of curves in different types of spaces, and we're going to start moving towards coming up with a rigorous understanding of different kinds of homotopic curves in different kinds of spaces. But R2 is not really the space to look in to explore this, because every curve is homotopic to every curve connecting A and B is going to be homotopic to each other. However, there is an important point we should talk about, which is the subspaces of R2, right? If we go into R2 and we have, I'll draw two different subspaces. I'll draw this subspace, and I will draw this subspace. I will draw this subspace. How about something like that? So the difference between these two subspaces is this one is convex. This is all in R2 still, right? And this one is not convex. And the idea is that in R2, if you have any 2 points in a convex subspace, the line connecting them, the straight line connecting them, and you can talk about a straight line in R2 because it's R2, right? Every point is an ordered pair, AB, because R2 is defined as R cross R, which is the set of all ordered pairs AB, right? Where A comes from the first R and B comes from the second R. So everything is A and B, and all we have to do is make a function, like t of x plus 1 minus t. Well, I shouldn't use t, I should use, that was confusing, right? I should say s of x plus 1 minus s of y. When s equals 0, the point is x. When s equals 1, when s equals 1, the point is x, and when s equals 0, the point is y. So it's actually, this is a curve going from y to x. So, and x is an ordered pair AB, and y is an ordered pair A1, B1 or something. So you can always create this line. That's my point. This is the line. And the point is, in a convex set, that line will always be inside the set, no matter where it is, right? Even if you go up here, and if it's designed right, maybe that should be up a little bit, right? Because otherwise, like for example over here, those 2 points, the line has to leave the set. I almost drew this, my convex set almost had an example where you could leave the set because it bent down a little bit. But the point is all convex sets in R2, you can draw a straight line connecting the 2 points. But the point is any path in a convex set that's inside the convex set will be homotopic to any other path inside the convex set. But now the way I've driven it, the same could be said of this set here, right? Just because that line doesn't fit the definition. Any path inside the set is homotopic to any other path that's inside the set. So in this case, if I drew this path, that's inside the set, and certainly this path is inside the set, and those two look kind of homotopic to me, right? So what's the difference between a convex set and a non-convex set? And the answer, of course, is I've drawn a bad example of a non-convex set for this purpose. In that case, it's also true of the non-convex set. So you can be homotopic inside a non-convex set. It's just not every one of them. In this case, every convex set, it will always be true. But in this non-convex set, I'll do it like that, but also I'll put a hole in it. Now, all of a sudden, you do have a problem with being homotopic inside this subset of R2. And the problem is, if I have this point A, and let me draw the hole so you know that that's not part of the convex set, and this point B, I certainly can draw a line from A to B like that, and there are plenty of paths that are homotopic to it, right? There's one, for example, right there. But if I draw this path that goes this way, now all of a sudden I have a path that's not homotopic to A and B inside the set. In fact, it's still homotopic in R2 in general, right? Because R2 in general contains all the points, including this stuff that's missing. But I'm just thinking now about this convex set that's this set here missing this. It's also missing everything outside, of course. And the path now, I cannot continuously deform that path into A and B. So in this convex set, there are two different types of homotopic paths from A to B. And so, so subsets of R2 is definitely not the same as R2 in general. Likewise, I can draw yet another path here. It's not just the fact that there's two paths. It's not that there's two different homotopic collections here, right? I'll call, you could call this a homotopy of all the homotopic paths. We're going to talk about the equivalence relation between homotopic paths in a moment, but all the paths between A and B that are homotopic to this black one, and then you have all the paths that are homotopic to this green one. Are there any others? And indeed, there are others. There's this blue one, right, where I go all the way around this thing and then go to B. And that's not homotopic to either of those, right? And in fact, I could do it again. There's nothing to stop me from going from A and around twice, right, to B. And that's not homotopic to the blue path, actually. So there's actually, in this simple example, there's an infinite number of homotopic families of paths between A and B, and they all have to do with the number of times you go around the center. So that's just an example of why, even in a plane R2, as long as you're dealing with a certain kind of subset, you can start generating many different types of homotopies, despite the fact that when you look at it in this sense, it's hard to understand why two paths would not be homotopic to each other. But in fact, this whole really makes all the difference. And in fact, a lot of algebraic topology, arguably all of algebraic topology, is about a way of using group theory to describe the fact that certain topological spaces have holes or things similar to holes in it that disrupt this simplicity of the universal homotopy of all curves between A and B that you might get in the plane, say, and make it so that there are now a large number of different homotopic families of curves between 2 points A and B. So actually, we should formalize the meaning of families of homotopies a little bit, and the way we'll do that is I'm going to, I guess I'll be doing this A-B drawing a lot in this little lecture. But we know that A and B is homotopic. Let me throw in a hole here. Let me make my hole a different color, I guess. So let me throw in this hole, and then throw in another homotopic path here. So I was talking about families of homotopies. Well, it turns out that if I call this, say, gamma 1, then I create another path here. I call that the black family of homotopies, and I call that gamma 0. And I know that gamma 0 is homotopic to gamma 1. Well, what's interesting is gamma 1 may very well be homotopic to, say, gamma 2. Gamma 1 is homotopic to gamma 2. And I certainly know that gamma 0 is homotopic to gamma 0, and I know that gamma 1 is homotopic to gamma 1, and I know that gamma 2 is homotopic to gamma 2, for example. That's trivial, right? Every curve can be immediately deformed into itself. I know that if gamma 1 is homotopic to gamma 1, I also know that gamma 1 will be homotopic to gamma 0. Likewise, if I know that gamma 1 is homotopic to gamma 2, I'll know that gamma 2 is homotopic to gamma 1, right? I mean, there's nothing, this shouldn't be too hard to see, but, if I can deform gamma 1 to gamma 2, I just run the homotopy backwards to get the opposite homotopy. That is, if f of s and t is the homotopy between gamma 1 and gamma 2, then f of s of 1 minus t is the homotopy from gamma 2 to gamma 1, right? I just run the curve in the opposite direction. Or I run the transition between the curves in the opposite direction, from gamma 2 to gamma 1 instead of from gamma 1 to gamma 2. Likewise, I can run a curve from B to A instead of from A to B. We'll talk about that in a moment. So the point is the fact that this is true here, the fact that these are true, means that the homotopy is reflexive, right? It's reflexive because everything is homotopic to itself. These two, that gamma 0 is homotopic to gamma 1 and gamma 1 is homotopic to gamma 0, those two mean that homotopy is symmetric, right? And then the last one we want to remind ourselves is that if gamma 0 is homotopic to gamma 1, which is that, and we know that gamma 1 is homotopic to gamma 2, which is that, then it's pretty clear that gamma 0 is going to be homotopic to gamma 2. And again, you can show that. The way these proofs always go is you play with f. If f of s and t is the homotopy from gamma 0 to gamma 1, and h of s and t is a homotopy from gamma 1 to gamma 2, it's not too hard to combine these variables into g, right? And g might be of s and t, and g of s and t is a combination of f and h, where you're actually creating a homotopy from gamma 1 to gamma 0, then gamma 0 to gamma 1, then gamma 1 to gamma 2, all at once, right? So you basically have to take your t, and you have to sort of you have to go twice as fast, right? You have to go, I think, let's see, it would literally look like this. It would look like g of s of t is going to be f of s and 2t for t is greater than or equal to 0 and less than or equal to 1/2, and then it's h of s, and then I think it's 2t minus 1 for 1/2 less than or equal to t less than or equal to 1, right? So let's see, if t is equal to 0, then if t is equal to 0, then g of t equals f of t. When t gets to 1/2, g of st equals f of s and 1, which means g of st now equals gamma 1, right? Because f of s and 1 is the curve gamma 1. And then when when t equals 1, then it equals h of s 1 times 2 minus 1 of 1, which is gamma 2, of course. So it's transitioned between gamma 0 and gamma 1 by the time t gets to 1/2, and then it's gone from 1 to 2 when t equals 2. So this is now homotopy between gamma 0 and gamma 2. That's to prove this point here, which is that we have a transitive. It's transitive. So we've got reflexive, symmetric, and transitive, which means the property of being homotopic is an equivalence relations. It's an equivalence relation. And that's important, because now I can free myself from talking about a single homotopic curve, and I can talk about all the curves. This is the set, right? This is going to be, let me move this down here. This is going to be the set of all curves homotopic to gamma 0, right? And that is the equivalence class. And we discussed this extensively when we talked about quotient spaces. So already this idea is a big help, because now when I look at this situation here, I can now talk about all the paths that are the equivalence class of the gamma 0 paths. And although I didn't give this one a label, I could call it, say, well, you know what, I'm not going to use gamma, I'm going to use, say, alpha. And I could talk about the equivalence class of all the alpha paths, well, alpha 0. And remember, inside here, inside the brackets that describes the class, I can put any representative, right? Because clearly this is identical to, say, gamma 1, right? Any representative can call out the entire class. So right now I have two equivalence classes of homotopic paths. I have the equivalence class just with the representative gamma 0, the equivalence class with the representative alpha 0, and then of course I can do all of these other things that I was talking about before, which was, well, I'll keep it with green, the equivalence class where we go around one full time, right? And I could call that beta 0. So we have the equivalence class beta 0. And then, of course, you can imagine each number of orbits of that circle or of that missing disk will be another equivalence class. So I can, alpha, beta, I could have equivalence class. I've already used gamma, so I could have equivalence class, say, delta 0, etc., etc., etc. And clearly, there's basically your intuition on this is there's going to be an infinite number of equivalence classes, one for each orbit around this central piece, right? So we've already kind of described something about this space. And what space is that? I guess it's the space of R2 with a hole removed, right? So if I kind of draw out this hole like that, I wonder if I can, let me try something. Let me see if I draw, make my thickness bigger. Yeah, I can sort of draw out the hole, right? Make it a little bit of a black hole here, I guess, right? This is this missing piece of the space. Go back to the normal thickness. And so now I'm talking about a different space, right? Imagine I'm talking now about R2 minus D, where D is this disk here. I didn't leave any room to write. Oh, I can do it in red, right? This is D, right? So that's a different space than R2, right? And clearly, the first thing we notice is that we now have, instead of one homotopy class, right? Instead of having just the equivalence class of all curves gamma between A and B, where they're all the same, now we actually have an infinite number of homotopy classes. So we have gamma, and then we have alpha, and then we had beta, and then I guess we had delta in there, right? So these two spaces, just by the presence of that hole, this huge effect happens on the number of homotopy classes. So clearly, this idea of homotopy classes immediately tells us something, is very sensitive to this change in the topological space. So this change in the topological space has a big impact, and not only, I guess, saying that has a big impact, what I mean to say is that we have a device, or we have a hint of a way of measuring something about the space by looking at these homotopy classes. So now a lot of the time we spend in studying the homotopy theory is to sort of flush that out mathematically. What can these homotopy classes tell us about this space, or what do they report about this space? And a lot of this has to do with how do we identify spaces that are homeomorphic. If I find some space that's homeomorphic to R2 minus D, will it have the same homotopy classes as R2 minus D? And likewise, another way of looking at it is, if I find a space that has the same homotopy classes as R2 minus D, is the R2 minus D homeomorphic to that space? And it turns out that the answers are not the same, right? Homeomorphic spaces will have identical properties regarding these homotopic paths, but spaces that have identical properties regarding homotopic paths do not necessarily have to be homeomorphic, which is sort of a little bit of a lament whenever you read a textbook on homotopy theory. They wish that was the case. That was the big hope, was you could use group theory to understand all of topology, but instead you can only understand portions, and you learn new things, but you don't understand, it doesn't break open all of topology into group theory. In other words, topology and group theory are not corresponding one-to-one subjects in any sense. Okay, so now let's see if we can put these things together in some kind of logical structure, and that's going to be the next step. All right, so here I've drawn in advance, I don't usually like to do this, but I've drawn in advance a couple things. I've gotten now 4 points, A, B, C, and D. And I've created a path from A to B that I call alpha, and we're now thinking about the entire equivalence class of all paths that are homotopic to alpha. And then I've created a path from B to C called beta, and its equivalence class of homotopic paths, and gamma, and its equivalent path of homotopic paths. So we have these 3 equivalence classes. Now, why are they? They're different because their endpoints are different, right? B goes from B to C, and that's not A to B. So under our current understanding of homotopy, this path here is not homotopic to this path because it doesn't share the same endpoints. And that's a huge deal right now. As we move on, things get broader and broader. For example, as we move on, first of all, A and B become the same points, and we're interested in loops, right? That happens later. And also, this curve and this curve indeed are related by one of those more broad homotopies where I'm allowed to move C around, but not for now, right? For right now, we're keeping the endpoints fixed. So, but what I want to do is I want to be able to somehow combine this path and this path together. And again, we're headed towards algebra, right? And algebra is big about that. If I have an object and another object, I should be able to take the product of 2 objects if I really want to jump into something like groups and try to create groups. I need to be able to create products of things. So how do we do this? Well, we've already basically done it, right? If I want to create the product of A and B, I might define it this way. I might write it as alpha beta is going to be a new path. It's going to be a path from A to C, and it's going to be alpha of 2s and beta of 2s minus 1. And this is when s is greater than or equal to 0 and less than or equal to 1/2. And s is greater than or equal to 1/2 and less than or equal to 1, right? So what I'm basically doing is I'm starting here, and I'm running twice as fast as normal to there, right, 2s, and then I run twice as fast as normal to there, and so ultimately I end up with a curve where s goes from 0 to 1 between A and C, and it covers alpha first and then beta second. And I'm going to name that curve, alpha beta. And what's important now to understand is although I've created one curve using alpha and using beta, this will work for any curve in the homotopy of alpha and any curve in the homotopy of beta. So I can, and then that final curve, it will have its own homotopy class, right? So what I want to be able to say is that the homotopy class of alpha multiplied by the homotopy class of beta, that definition of that multiplication is the homotopy class of alpha beta. So what this means is alpha is just the representative, one representative of the homotopy class. Beta is one representative of this homotopy class. Alpha beta is the representative of this homotopy class. And indeed, any I can recover the entire homotopy class of alpha beta by taking this product, and this product is defined. So that's a set, and that's a set, and this is a set. The idea of taking that set and multiplying it by that set is defined by going to the homotopy of the curve represented by AB and finding that homotopy class, and that's how we define multiplication of these homotopy classes. So that's very critical. Now I have this other curve gamma here, right? So there's nothing to stop me from writing alpha, beta, gamma, and obviously it's going to be the same thing. Oops, but it's going to be such that I use a 3s, right? I go 3s and then 3s minus 1 and then 3s minus 2 or something like that, and I ultimately get a trip that goes all the way from here to there, while s goes from 0 to 1. And so you can do any number of products together, and it will always be the case that alpha beta gamma will equal the homotopy class of the curve represented by alpha, beta, gamma. But perhaps more importantly for the concept of group theory, which is where we're headed, it has to be the case, groups, by the way, you may remember are associative, so alpha, beta, gamma is certainly equal to alpha, beta, gamma, right? So we've got that. Also, we should quickly talk about the inverse of a path, right? So a path from B to C, we certainly can make the inverse path, which we could call beta inverse, which is just the path from C to B, right? And beta inverse, it's actually a different path, right? Beta inverse from C to B it could be the exact same path, which, for example, if it's beta of 1 minus S is really what it would be, right? So, so a path from C to B is a different path, right? And so if we wanted a path from B to itself, we might very well go from B to C and then back, right? That would be a path that would look like, that would be a path with the endpoint. And we are going to talk about loops, but a path from B to itself is obviously just sort of ultimately just staying at the point B. So we have inverse paths, we have associativity, we've defined the product, of course, and all this gets around to the critical point that we're creating a group here. We're creating a group structure. But we don't have quite everything we need to do that yet. We need to actually narrow down our concept of paths, because there's just too many. Because there's one for every pair of points, there's a homotopy class of paths, or multiple homotopy class of paths, right? For example, in this multiplication, I talked about A and B, but there's another homotopy of paths from A to B, which I guess I could, do this way, right? So that would be, say, A prime, and clearly A prime beta is certainly not equal to, I should say, alpha prime beta is certainly not equal to alpha beta, right? But so just to be clear, right? The fact that this whole is here is relevant to this discourse, right? The way I've described everything here, we really never made much reference to the whole. But of course, the fact that the whole is there means that there's different homotopy paths from A to B, likewise from B to C, and even from C to D. They all have multiple this isn't trivial stuff, right? Because there's not only one homotopy path. So the whole being there gives us a way to illustrate that. But now we need to move on and see how we can construct a group out of all of this. So the way we're going to do that is we're going to restrict ourselves a little bit. And we're going to now, instead of talking about A and B, we're going to talk about a loop, right? And I'll just take the point B. I'll use B for like base point or something. And a loop is a path that goes from B back to B. Otherwise, it's exactly the same as what we've discussed, right? There's still, this is still a path, so we could call it gamma. We could call it gamma 0. And then there's another path out there, perhaps, called gamma 1, right? And gamma 1 and gamma 0 can be turned into there is a homotopy between gamma 1 and gamma 0, just like before. It's still going to be a map from 0, 1 cross 0, 1 to, let's see, into the space X, whatever space we're dealing with, right, where this is S and this is T. And so, and it's still going to be true that F of S of 0 equals gamma 0 of S, and F of S of 1 equals gamma 1 of S, and it's just like everything else except now that the two endpoints are the same. So these are loops. And just like the fact that two endpoints are the same, you're still going to be affected by holes in the space, right? If you have a hole in the space right here, gamma 0 and gamma 1 are not going to be homotopic, and no such function is going to be possible to make without breaking. No such continuous function will be possible. But if the hole is out here instead, and not in there, well, in that case, those two paths would be homotopic, right? So the holes still matter. It's just now that we're dealing with loops. Likewise, the products. And, let me throw down a hole here just so I can create different homotopies, right? Right, so now I'll create this homotopy like that, right? So there's that one that goes around once, and then how about a green one that comes out and sort of goes like that, right? So there's several different paths there. And just like before, we're dealing with one point, we can still combine these things, right? So I'll call this green one alpha, and this blue one beta, and I can still create beta, say, alpha, right? I can still multiply them together, and I still have the same rule. It's going to be equal to beta alpha, where you traverse beta first, right? You go this way, and then you traverse alpha, right? And then that creates a new path that is this sort of double traversal, and we know that path is going to have its own homotopy class. So now we still use the same multiplication idea. It's still going to be associative, and you're still going to be able to do inverses, right? You just traverse the path in the opposite direction. And then there's also the constant path, right? The path where you just never leave B and you just sort of stay there, right? So you have this identity path that doesn't change anything. And now you have all the parts to make a group. And that group, remember, a group is just a set, right? Everything is a set in this business. So a group is just a set of all the homotopy paths. It's a set of all the equivalence classes of homotopic paths, right? So every possible homotopy path has an equivalence class, and we would put every one of those equivalence classes in here. And for the space with this one little hole here, like I've drawn it, there'll be a countable infinity, right? Right now we understand all these orbits, right? And you can only orbit an integer number of times, so you can count that. So at least this time it's countable infinity, right? So that's good, right? So we have this countable infinity of equivalence classes. That set is going to be our group G. Actually, I'm not going to call it G. I'm going to call it pi 1, right? This is called the first homotopy group. It's also called the fundamental group. The fundamental group. It's the fundamental group of the space X, of that topological space, right? And so this fundamental group is all the homotopy paths of loops, right? These all have to be loops at B, right? So, in fact, what I really should say is I should define this as pi 1 of the space X located at the point B, right? That's the more correct way to say it. That's not enough information over there. You need to know everything. You need to know the space involved. You need to know the point where all the loops start and stop. And the 1, that's something we'll worry about later, but it's just, there's other versions of this. This is the first version involving the most simple structure we have, which namely are the loops. It's also the most important group, so you could think of it as like the number 1 important group, I guess. But it's called the fundamental group of this space. So this is the fundamental group. Now, a group has the multiplication property, but we've already described that. It has an identity, which is the constant. It has an inverse element for every element, which is just the paths going in the other direction. And it's associative, which we showed. So this is actually a group. So now notice that there is one of these groups at every point in the space, right? If I have this space point B, and then I have a point E, then I have a point F, well, and then maybe there's some piece of the space missing, right, like here, say, each of these sets has their own collection of homotopy paths, right? And they all explore the topological space, starting and ending at that point. They're all affected by the same holes in the space, right? Right? But there's a group at each point, right? There's a group here, pi 1 x e. There's a group here, pi 1 x f, and pi 1 x b, right? So there's a group at every single point, which is a bit burdensome because it seems like, you know, look, all these groups are probably the same, meaning these groups are all going to be isomorphic, right? Any point in this connected region, all the groups will be isomorphic, right? And that relationship between groups, isomorphic, just means this group is the same as that group, it's just all labeled differently. And you can actually prove this pretty rigorously, right? Because what you can actually say is something that's almost shamefully obvious. Let me put it there. But we know that if I have some other point, h, I could create a path between E and H, right? And then H has its homotopy group, right? It's a bunch of, it's a fundamental group there. But I could essentially start at E and go to H and then make this loop and then go back to E, right? And by doing that, I can basically translate these groups all over the plane. Because what I'm doing is I'm starting at E, and say this path here is called, say, delta. I take delta, then execute a loop, and then I take delta inverse back, right? So say the loop I execute here I call gamma. So what do? First I do delta, then I do gamma, and then I do delta inverse, right? And that's really a loop at E, right? That starts at E and ends at E. So that's essentially another loop. So I've basically incorporated all the loops here to the loops there. The point I'm trying to make is that I can really think about the fundamental group of the entire space without the base point, because all of the base point spaces are isomorphic. And you can prove this by just sort of connecting them together with paths, right? As long as these paths are ultimately in the same connected component of the ultimate set. Now we should say that, strictly speaking, right, the elements of the group, the elements of any of these groups, they are these homotopy classes, sure, but they're also group elements themselves. So we usually will speak of a map between homotopy classes and group elements, right? So, for example, if I want to describe the isomorphism between pi 1 of x and b, I need a map between pi 1 of x and b and pi 1, or the fundamental group of x and e, right? I need a mapping. And sometimes that mapping will be called, say, this requires its own map, right, between two sets, and that mapping is an isomorphism in the case we're talking about now. And therefore, since all of these sets are the same, I can think of the abstract group fundamental group for the entire space, because all of the points in the connected component will have the identical fundamental group. All right, so that's an important point, is we can actually talk about the fundamental group of the topological space. All right, so now that we're talking about loops, well, there is a nice advantage to this, and that if I take a point B and I have a loop at B, this path at B, I can actually think of it not only as a map from 0 to 1 into X, right, which is sort of what I'm doing, but it's a loop now. So we know that the endpoints are the same. So in some sense, whatever value for the function, for whatever this function is, say I call this function alpha, right? The alpha is this path, this loop path. Whatever this function is, its value at 0 and its value at 1 have to be the same. So in some sense, I could actually think of this as 0, the interval 0, 1 with the point 0 and 1 identified, right? Which is the quotient space of the interval 0 to 1 with 0 to 1 identified. But that, we know, is homeomorphic to the one-dimensional circle. So I can now, if I'm dealing with loops, I can say that alpha is actually a map from S1 to X, because the loop, the nature of it being a loop, converts this interval actually into this quotient, because again the value at A0 and the value at A1 has to be the same, so I could actually identify those 2 points, right, and I end up with the circle, and then I can make this a map from the circle into X, only if, of course, if it's a loop. And so I could actually write something like alpha of S is some function of E to the 2 pi is, right? Because that's sort of the way we describe the circle, right? And when S equals 0 and when S equals 1, the argument is the same, right? So I get f of 0 is equal to f. This all implies that f of 0 equals f of 1, right? So I have to make it so that this equals the point B, right? So this is and so f is now a function from S1 into X, right? S1 into X. And so this is just another way of looking at loops that's a little bit easier sometimes. You think of it as the map of a circle to X. It's kind of obvious, right? You're dealing with a loop, right? And so surely it's this path here is going to be homeomorphic to a circle, and you likewise, you have the same issues of having a hole in the space, right? You can still have this function can still wrap around the hole, or it can miss the hole, or whatever. So that's just another way of looking at this, using S1 as represented in the complex plane by e to the 2 pi is. Also, as an aside, if you start reading some of the literature, sometimes you'll see the notion of a pointed space. A pointed space. And this seems almost sort of silly, but the set, not the set, but the collection of a topological space where you identify one point as just special. You just highlight the fact that there's a specific point in the space you want to talk about. Sometimes you call that a pointed space. And that comes up in the study of homotopy because these loops are often identified to be happening at a certain point. So I want to say a pointed space. So I'm saying a space and a point in that space. And now I'm talking about a map from that, say, to another space with a point in that space. And this map F, from pointed space to pointed space, it usually has the rule that f of b equals e, right? So you'll see this often in sort of the literature on homotopic spaces. And in fact, we'll use this notion of pointed spaces to come to our last topic for the day, which is the notion of induced homomorphisms between the fundamental spaces of two different pointed spaces. So I have our topological space X with its point B, And I'm going to define a function that takes that to a different topological space y with its point. Wait a minute, let me do it this way. Its point C and this point B, right? So that means that whatever this function is, f of C equals B. There's nothing super special about the points C and B. I'm just highlighting that I'm singling out a point in that space, and this function is going to definitely take C to B. It's sort of an economy way of writing. It's sort of an economy way of writing x with a point C and y with a point B, and then a map f, and then f. Oops, that's C. F of C equals B. Right? It's an economic way of writing all that down. But actually, let's go ahead and not be economical for the time being, just because we want to be clear here. So this is the space y, and this is the space x, and this is f of C here, which is actually equal to B. And here's our function f. Well, C is a point that has its own fundamental group, right? And B is a point that has its own fundamental group. And now you kind of see why this notation comes into place. I need that y to show that this fundamental group is acting in y. If f is a continuous function, if x is a continuous function from x to y, and we know how to define continuous functions using our point set topology, right? Remember, it's 1-to-1 onto, and F inverse maps open sets. F inverse is open. It maps open sets to open sets, right? So if F is continuous, then what we want to show, or we want to, well, what we will know, is that the fundamental group at C and the fundamental group at B, these two things are going to be homeomorphic. Whoops, I screwed that up. Homomorphic, right? These are groups. See, I'm talking about groups and topologies all at once. So this is homomorphic. These are going to be homomorphic groups. So if the spaces are connected by a continuous function, x to y, then the fundamental group at B is going to be homomorphic to the fundamental group at C and X. All right, so let's see how this would actually work. I will redraw this. This is going to be, let's see, I'm going to call this space Y, and it's going to have a point in it C. So this is YC. And then I'm going to call this space X, and it'll have a point B, right? And then there'll be a function f from y to x, from the space y to the space x, and the point C will go to, of course, f of C, which equals B. So that is our map. So f is a map from y C to x B, like that. Now, once we have that map, we want to create another map, which we're going to call f with a little star on it, and that map is going to go from the fundamental group, which is a set of y at C, to the fundamental group of x at B. And there's a couple of attendant things around here, right? We're going to have, imagine a loop here, which we would call, say, alpha, right? And the equivalence class of alpha is an element, is basically an element of pi 1 of the fundamental group at C, right? Because alpha is a loop, and this is a group of equivalence classes. This is a set of equivalence classes, alpha being one of them, with these group operations that we described before in the previous part of this lecture. So now this fundamental group contains as elements equivalent classes. and one of them would be the curve alpha. But you now have a curve, you now have this function f, right? So you can imagine taking this curve alpha and projecting it onto its image in x using the function f. And you'll end up with some curve over here. And that curve is going to be alpha composed with f, or f after alpha. So you also, I guess we have to remember here that there's some circle, S1, right? And then there's a map from that circle, S1. Basically, that's what the map alpha is, right? The map alpha is a map from S1, where that's the point, say, 1, right? And we can make this on the complex plane or something, just some articulation of the circle. And then we map alpha, and alpha ends up projecting to be this. So alpha is a function of s, right, through e to the 2 pi I s, which is the circle. So now we map from the circle onto here and then project with f, and that's what this is, right? So ultimately this thing here is a function of s. And it's a curve in this plane, and it'll be a circle. And so the point is that the group element f star of the equivalence class alpha is going to equal the equivalence class of f compose, or f after alpha. So this side is so this guy in here, this argument, that is an element of this set of the fundamental group of y at C, and this function takes members of that fundamental group and returns members of the fundamental group of x located at B. Well, one of the curves of x located at B is f after alpha, just like this, operating on s, right? S, taking s as an argument. Well, that's exactly what this is, right? So the mapping for the curve alpha is just the equivalence class of which f compose alpha is a representative, and that's this thing. And that's how this mapping actually works. So the mapping under the continuous function f, which we call f star, which is a mapping between the fundamental groups, is going to be basically you take the equivalence class of the curve, and that is going to map to the equivalence class of that curve composed with f, which puts it in this space x. All right? And then it doesn't take too much effort. It does not take too much effort to discover all the important things, which is, all the important things regarding these kinds of mappings, that f star of say alpha multiplied by beta is going to equal f star of alpha times f star of beta, right? And we'll also be able to discover that f star of alpha inverse, right, going around the other way, is going to equal f star of alpha, right, the whole thing inverse, right? And the if you have a constant map, f star of, see the point C, right? That's what we're calling it. We're calling it C. F star of the constant map is going to equal f star of f of C, right? Which equals, by definition of how this was designed, f star of B, right? And so basically, what this ultimately shows is that this map here is going to be a homomorphism. It's a homomorphism between pi 1, y, c, and the fundamental group of x at b. And so that's a pretty big show, right? We've been able to show that a continuous function, defined topologically speaking, is going to induce a homomorphism between the fundamental group of this space at C and the fundamental group of this space at B. And of course, remember, this is not a trivial statement, except the way I've drawn it. I've left out the fact that there could be holes in these groups, right? Maybe even more than one. And look, if I have a two-holed group in a continuous function, you're going to see that it's not a one-to-one correspondence, right? There's going to be paths in here. There's more homotopies available in this space because there's two circles, right? You can imagine going around one, then around another, or around one only, or not around either. But here you can only go around one. So the group, the fundamental group over here in this circumstance, is going to be a bit smaller than the fundamental group over here. But that's okay because we're dealing with a homomorphism, not an isomorphism. Not an isomorphism. However, it does turn out that if F was an isomorphism, right, and I'll make it that way by maybe adding another circle here and claiming that F is a homeo. If F was a homeomorphism, it'll turn out that F sub star is going to be an isomorphism, right? So when two spaces are homeomorphic, their fundamental groups are isomorphic. But when two spaces are just connected by a continuous function, then their fundamental groups are going to be homomorphic. And that's still pretty good, right? That still makes a connection between them. So therefore, we've come pretty far. We've defined what we've defined what homotopies are, and from that we've explored a little bit about how to create an algebra of homotopies, which is the fundamental group of a space. So we'll explore this more in our next lecture, and we'll start articulating some important things about how to describe this fundamental group, and things about covering spaces, and then slowly work our way into a few examples.